It is not well described in your textbook in this chapter, as well as I wanted to see. That is why I'm going to go through very meticulously, and we're going to use this information, I promise you, the moment we hit rotation. Before getting into the specifics of rotation, let us talk about radians. If this is a circle of a radius small r, and this angle here, theta, encompasses some distance, some part of the circle, which I'm going to use a different color. I'm going to call this S. S is distance, meters. So theta in radians, careful here. Make sure your calculator, make sure you know where the radian mode and the degree mode on your calculator live. Very, very important. The theta in radians is going to be equal to the arc, the distance of this segment, divided by r. Note, units, I'm sorry. What is the units for distance? Meters. What is the units for radius? Meters. What are the units of radians? Radians are not units. And here's the proof. Radians are just a percentage, if you will. You with me, guys? Now, radians and degrees are the same thing, are a different sort of percentage. We got 360 degrees or 6.28 radians, 2 pi, in other words. Yes, pi in radius is 3.14. That's it. You can convert back and forth between radians and degrees, but from now on, degrees, kiss them goodbye. It's about radians. A quick conversion is that 1 radian is about 57 degrees. Okay? But again, we're going to stick with radians instead of degrees. And why is that? The reason is this next part. Now I'm going to draw another circle. And this particular time, we have an object that is moving along this circle. The important thing is that its speed is linear speed. Since it is moving along a circle, it is always going to be perpendicular to the radius of this trajectory. I'm going to call this U. And this little r. Now it is eventually going to move to another location where its linear speeds, I'm choosing it to be constant. The magnitude, not the vector. The vector changes, right? Eventually it's a circle. But the magnitude will remain the same in this particular case. So let's say that within some time delta t, it goes over some angle delta theta, which is this guy. Can you guys see the colors? I'm not sure if this blue is okay. All right. I know some of you guys have problems with colors, and I know it's, but if you do come and see me in private, and I'll try to figure something out, okay? So what did we learn a second ago? This is what we learned a second ago. That my angle, my delta theta, is equal to what? The distance that this object covered S, yes, divide by my radius R, yes or no? Yeah, yeah, but so we can write this as the distance equals delta theta times R. Okay, big deal. But at the same time, though, isn't this, we said that U is constant, the velocity, linear speed is constant. So it is essentially covering a distance S that is going to be equal to what? U times delta T, yes or no? You with me, guys? Make sense? Nice. Can we divide the two? Yeah, we can. Of course we can. What do you get? What do we get? Delta theta over delta T equals to the linear speed over R, yes or no? From now on, this physical parameter, we are going to give it a special name. We're going to call this the angular speed or velocity omega. And we're going to write omega equals to UR, or the linear speed equals to R times omega. Now, there is more to this than meets the eye. Let me ask you something, guys. If I were to consider, there is a problematic issue. U is a vector, yes? Yeah. What about R? You can conceive it as a vector, right? What of omega? Well, let's see. Can somebody tell me that what U dot R is? That is a dot product. Excellent. For a circular, as long as we're dealing with a circular motion, yes? This is zero. These are perpendicular, yes? Now, if these are indeed perpendicular, we can also write that U is R cross omega. And yes, indeed, omega is a vector. We're not going to be using its vector properties. Why is that? What is the direction of omega? Right-hand rule, yes? What is going to be? The middle finger. Careful, make sure you lift all three. You with me, guys? Omega is going to point, in this particular case, where? Look, index finger, my R. Middle finger, my U. Omega is into the board. You guys with me? So omega is pointing inwards. Somebody's going to ask me, okay, dude, so what's the big deal if we call omega a vector or not? Right now, it's not obvious. Right now, you cannot see why it's not important to call omega a vector. A month from now, you're going to change your mind. You're going to see why omega is very important to call it a vector. All right, guys. For now, we keep it in the back burner, the linear speed, but this, we need to write it over and over again, the linear speed or velocity equals to radius times the angular speed. This is the first, or rather the second bridge that we are building between something that moves from left to right, aka a linear motion, versus something that moves along a circle, aka circular motion. The first link, the first bridge that we built came from here, from basic trigonometry, right? This is how we derived it. And the second one is this guy in its vector form. Omega has units. What are the units of omega? Well, let's see. Omega is what? U over, U over R, right? What are the units? Meters seconds over meters? Seconds the -1? Yeah, well, not quite. We're gonna stick in radians per second. You with me, guys? We good? Now we said that we derive this as when u, the linear speed, is constant. When linear speed is constant, we call this uniform circular motion. And the question that I have for you is, do we use this expression only for uniform circular motion? Absolutely not. If my u changes, my omega will change also. You with me, guys? It doesn't matter. This is a genetic link, not in particular constrained for or constrained to uniform circular motion. It can be non-uniform circular motion. Let us solve a couple of numerical problems that they will build our confidence in this rotational stuff. Example. A particle is circling about an origin. Particle moves in a circle. At an angular speed, omega equals 0.2 radians per second. What is the linear speed? Find the linear speed at r at a distance, the distance vector 3,4 meters. I'm sorry. This at, yes. I use it pretty often, but it's, I don't know if that. All right, I know it doesn't look like an at. Okay, all right. You have, how about now? Okay. Muchas gracias. So, any takers? We know that U is omega R, yes? We know it's a vector, but we're dealing with magnitudes here. We know that omega is either into the board or out of the board, yes? Yes. So how do we go about finding? The only thing we need to find here is what? R, yeah? What is R? R is the magnitude of the vector, right? The radius. But at that point, do we know the radius? What is it? Isn't this the case? Yeah. That's it. 5 meters. Therefore, the linear speed is 0.2 times 5, 1 meter second. Now, open your ears as wide as you can. I'm going to say something extremely important, which you're going to see that in the lab. You're going to see that in the lab final. You're going to see it in the lab in the final of this course. You're going to hear me say that 1 million times. How many types of circular motion did we mention that we have? 2. Yes. Let's write it down. The uniform, where U is constant in terms of magnitude, right? Because the direction changes. Eventually, it's a circle. Yes. And non-uniform, where U is not constant. No matter what type of circular motion we are dealing with, there is always no matter what type of circular motion we're dealing with, uniform or non-uniform, we are always going to have the so-called radial acceleration. This, to some of you, is also known as a centripetal acceleration. Seeking center. Why is this seeking the center? I'm going to sketch another circle. And this is my object, is moving at a constant linear speed in terms of magnitude. I don't need to repeat that. Yet again, the direction always changes. The direction always changes. The radial acceleration, it is going to be a vector that will be always pointing to towards the center, A sub r. Radial or centripetal acceleration, this is the same term, the same physical variable. It is going to be pointing towards the center and equal to the linear speed at that particular point. Well, if it's uniform, then it's the same U divided by the radius r. Substituting for U equals omega r, we get that the radial acceleration is also equal to omega squared times r. I'm going to repeat this last statement. No matter what type of circular motion we are going to have at least one type of acceleration. The radial acceleration has a direction always towards the center, aka the triangle seeking the center. And the magnitude is going to be u squared, the linear speed squared divided by the radius. And of course, if you substitute for u equals omega r, linear speed equals to the angular speed times the radius, then you end up with omega squared times r. I'm going to make a quick pause, and I want you to think of any questions that you may have. The question that I have for you, if you don't have any questions for me, is would you like to see the proof? How do we end up with this? Yeah? It is a little bit elaborate, but I think we can make it happen. Have you ever seen this proof before? So you must be thoroughly excited, right? Oh, come on. Come on, just, yeah, that's the spirit. That is the spirit precisely. Okay, now this little, it's not darts. It is and it isn't. Now, take a breath. I want you to focus on plot A, plot 1, this upper left. Yes. I'm gonna zoom in on this plot only. Yes. This is what I just sketched to you a minute ago. Circular motion, my linear speed, which is always tangential to my radius, goes round and round and round. Yay? Okay. My green arrow is my linear speed. My blue arrow is my vector, my radius vector, my radial vector. Yes? We good? We good. Now, wouldn't you say that, well, I can bring this vector, I can bring this vector, can take this vector and move it somewhere there, yes? As long as I'm not changing its direction, this is legit stuff, right? You with me, guys? Okay, so I have two vectors of velocity, yeah, which are different. Wouldn't you say that the delta V vector points towards the center? Yeah? Wouldn't you also say that, well, acceleration follows the vector of change of velocity? Yes or no? That's how we define acceleration to begin with. Yeah. So right off the bat, I know that this acceleration must be pointing towards the center. Yay? That's how we establish that acceleration points towards the center. It's not magic. It's just simple geometry. Plot number 3. Aren't we in agreement that these are the vectors that I'm messing with? Right? My V, my R, and my radial acceleration towards the center. Yes? Now let's put everything together. Do not panic. Wouldn't you also agree that I also have a delta R vector? Between the two positions, I also have one blue vector and another blue vector, but I also have delta R, yes? Like so, yeah? And I also have two triangles, yes? I have a triangle that is a, well, let me indicate the one triangle is this. And the other triangle is that. You with me, guys? Now here's where magic happens. You ask for the proof. And that's exactly what I'm doing. I'm giving you the proof. Now, geometry says, from triangle similarity, we get the following equalities. The following ratios are equal. Delta U divided by U, and I'm referring to these triangles, these two that are just highlighted. Delta U over U equals to delta R over R. Of course, all these are vectors. But guys, don't we also know that acceleration, which is also a vector, is delta U over delta T? We know that for a fact. Now, if we substitute this from here, what do we get? We get that acceleration is U delta R over delta T. You with me, guys? I just substituted. But hey, check this one out. What is delta R over delta T? That's. You with me, guys? Here's the proof. What day is it, Dave? It's Wednesday. I'll see you Friday.